morning, everybody. It's a great pleasure to introduce our distinguished speaker today, Mr. Sandeep Shukla from Virginia Tech. He is a very well-known figure in model-based design. Let me give you a few of his highlights from his biography. He's won some very prestigious awards, in particular the P-Case Award, which is extremely competitive. It's a presidential award for early career researchers, and the Humboldt Foundation's Bessel Award. He's a distinguished visitor and ACM, distinguished visitor of the IEEE Computer Society and the ACM visiting speaker and ACM distinguished scientist. And I think the talk that he will give today is very relevant to this colloquium. It's called Models of Time for Safety Critical Systems, Partial versus Total Order, Polychronous versus Synchronous. So please join me in welcoming our speaker, Professor Shukla.
Thank you, Shukla, for the introduction, and thank you, Mark and Shukla and John, who is not here, but hopefully you will see the video or something. So, all right, so what I'm going to talk about is something that I have been doing for a while now, which is to model software systems in a slightly different way than normally is done by synchronous programming people like Estro, Luster, or people who actually use things like Simulate, which is also a synchronous model of time. Now, model of time is a very important component of a software, especially safety critical system, because normally you don't do a sequential system for the entire safety critical system. What you do is it's usually distributed over over a network or a bus, like in an avionics or in automotive, and you have many processors running various components. And the question is, all these components have to communicate with each other, so they have to have some way of knowing how to synchronize. And this synchronization could be done in many ways. For example, you could do a highly synchronous design where you have a uniform global notion of time, created by a global clock or local clock, which are synchronized with some clock synchronization algorithms. And then your idea of your what time it is clear to everybody, and therefore communication becomes much easier. But the problem with that is manifold. Like, for example, time synchronization is expensive. But more than that, these days, when you do a time synchronization layer, chances of getting cyber attack on that layer is very high. And therefore, unless you have a very secure time synchronization technique, synchronizing time across all this distributed components is quite risky proposition. And therefore, the problem of synchronization has to be rethought in a way so that the programming model or your semantics does not so tightly depend on your notion of time, or at least not at every step. And the other issue is that compositionality. So nowadays, when you have large systems, you have to be able to compose pre-existing components for two reasons. One is obviously modularity and software use and all that, but also for formal verification perspective. If you have to have a monolithic system which has to be verified altogether, you have a state space equation problem, and therefore you have issue with that. Whereas if you have a completely compositional system, then verification as well as reuse and everything else is easier. By compositional, I mean that given two components, knowing their behavior, you can actually determine what would be their behavior when they are composed. And that should not depend on the implementation or delays in the system, in their communication and so on. So this should be deterministic when you compose them. So this talk, actually, first version of this talk was given last year around this time at the new clock workshop organized by NSF and various other organizations, where there was a dangerous proposition being preached by many people over 2 days. And that was to say that 1588, which is the IEEE standard for time synchronization over local area network, can be globalized, and there will be an femtosecond resolution timing across the United States and probably across the globe, and so that every programming model in the world will be based on a synchronized time programming model. So, and I asked them that, so to do this time synchronization, of course you are putting a layer, right? A time synchronization layer, this 1588 protocol layer. What makes you think that it will not be the main target of cyber attack? Because if you make your systems dependent on such a protocol, you are going to be vulnerable to cyber attack. And the answer was kind of a resounding silence, or it was more like, we are thinking about it, and we are talking about it, and so on and so forth. And in the entire 2 days, the only other talk that talked about security was a group in Texas Austin who are doing very good work on showing that GPS is also another basis for synchronization, which can do a microsecond resolution synchronization, but it can be easily spoofed, and therefore you can be sent to locations where you don't want to be at night. Or more importantly, for example, in smart grid, they have GPS time synchronization for measuring the voltage and current phasors, and use that to build the current state of the system to do the control. And if you can spoof them, then you can have disaster in power systems. So I think that it's a dangerous proposition to make systems such large global systems, distributed systems, based on a completely synchronous notion of time. Now, the time when I was giving this talk, few days before that, the CSEM, the Communications of ACM, published an article by Ivan Sutherland. He was a Turing awardee, and he's interestingly in support of my concern. The name of his article, the title of the article was "The Tyranny of Clocks: Promoting a Clock-Free Paradigm That Fits Everything Learned About Programming Since Turing." And there he strongly advocates non-synchronous systems, and mostly he concentrates on hardware design, where we know that the communication it has now overtaken the delays in their gates, and therefore communication to route the clocks throughout the large chip is very, very difficult, and therefore people are already talking about Gauss design, globally asynchronous, locally synchronous designs, and so on. But even then, there you have this problem that to cross the boundaries of one clock domain to the other is expensive, and also a lot of the power consumed in a chip is used in the clock network. So, but in general, having the time completely synchronized is in my opinion a bad idea, for various reasons, and some of the reasons may not be clear from this talk, but compositionality is one of the biggest reasons that I see is the problem. So what I'm going to talk about here is a partial ordered model of logical time. Now, I started by describing the notion of fully synchronized femtosecond time resolution. So you might think I'm talking about physical clock, but in software world, it's more than physical clock. It's more important to understand the notion of logical time or logical clock. And so we'll talk about that, and we'll talk about polychrony, which is what I work on quite a bit, and I'll describe this partial ordered model of logical time, and then I'll talk about some distinctions between synchrony, which gives rise to a total ordered notion of logical time, and polychrony, and then show that you can actually build a calculus in which you can actually reason about making deterministic implementation from polychronous models And then you can think about various tools and environments that you can build around this notion. And we are actually currently working with a company to build an industrial strength implementation of a synthesis tool that will allow you to synthesize multi-threaded software for various systems which are where the model is polychronous. So I guess here I don't have to repeat this, what a cyber physical system is. And I had a very interesting discussion this morning with Mark about cyber physical system. And so cyber physical systems have this sampling of inputs or measurements from the physical system, and then compute state based on the measurements, and then compute the control action that needs to be taken, and then do that actuation that basically does this control. And the physical system is dynamic, continuous, and have various modes and so on. Now, before I go ahead, let me tell you what we are not going to talk about. First of all, I'm not going to talk about modeling physical dynamics as dynamical systems. One of the problems there is zero crossing, how to model zero crossing. That's an interesting problem by itself. Real-time scheduling of reactions in data type systems, constructive semantics, visual modeling, and classes of synthesizable polychronous programs, and so on and so forth. So these are various research topics that come up as you actually try to implement and solve the problems of polychronous. So I have some papers listed at the end of the talk, which I guess the slides will be available to the students. So I think that you can actually look at these issues later. So let's look at this API controller example. I'll work with some very easy examples. So here is a car on a slope, and this the equation for finding out the thrust that you need in the engine in order for maintaining a continuous velocity, maintaining a constant velocity, is given by this simple Newtonian equation. And then by substituting some of the constants or approximating them, I got this. And then by applying the normal techniques of taking the Laplace transform and so on, I got this equation that says that the thrust U would be actually proportional to the integration of the error, weighted integration of the error term. Error term means that the instantaneous velocity that you measure with respect to the velocity I want to achieve, which is VR, and that's the error term. And then at the end there is a term that that's added over there on this side. So this is a very simple kind of a PI controller. So let's see how we are going to model this for software. So one way to write a software is very simple. You decide your 0 to t, that interval t, at what interval you will actually put the thrust, and then you are going to sample the current velocity, and then you continuously sum up the error with multiplied by the constant, and the constant, as you saw, that constant is dependent on the physical parameters of the car. And then you do this for a while until you have finished the time t, and then you basically compute the thrust, and then go back again to do the same thing again. So that's a pretty simple PI controller. Now, if you think about this, so from this program, it seems like it's so your inputs are actually the sample velocity, but if you think about it, this actually is a data flow, right? So as you sample the velocities, you are getting an infinite stream of velocities. And then as you compute the integral summands, that's an infinite sequence of summands, and the error term is an infinite sequence of error terms, and then you get an infinite sequence of thrust values, right? the U. Now notice that this U is not computed every time you sample a V. The U is computed only when the while loop finishes, right? So the rate at which the U is computed is different from the rate at which your velocity is sampled or other things are computed. So this infinite sequence of values we call flows, right? People call it streams or whatever. So you see that velocities, and then each velocity that you sample has a corresponding error term, right? So error term is basically V, the target V minus the current V. So that's an error term. So the arrows that I drew there show the correspondence. So every V I sample, I compute an error term. So they are always in lockstep. Every time I measure a V, I get an E. On the other hand, the U that I do is actually I compute the U after every n samples. So therefore the U1, U2 and so on, they are actually at a much lower rate than the other things. So I would call that as a subsample of the velocities, because I'm doing a subsampling of the velocities. So this is the first thing about this infinite streams or the signals, is that not all signals have values occurring on them at every time other signals have values occurring on them, and there may be some relationship between them. Now sometimes you may be able to establish this relationship because it's very simple. In this case, the relationship is that U1, every n times of V1, V's, I get a U. But in some cases, it may not be fixed. It may be dependent on certain other values of the parameters when you stop sampling V's and compute an U. So it may be actually not necessarily all that straightforward that it's an n factor of one another. So that's the notion of flows. So now, thinking of flows, now you can actually do the same computation that I showed you in a more iterative way. You can describe this as a data flow. So the data flows are actually a more correct representation, or not correct, but more relevant representation of this kind of infinite flow. So you have a flow of V coming in, and then you are computing a flow of E, and then you are counting. This count is actually always being reset to 0 after you're done with n, after you have done counting to n, and then you keep doing the sums, and then you do the U. But notice that this U has a qualifier which says when count equals 0. So when count gets reset to 0, only then I compute the thrust. So that shows that your computation of U is not at the same rate as the count or as the E or as the V, and that basically allows you to determine the different sampling rates at which these flows are either sampled or computed. So this is what it says. So this is almost synchronous programming, because you have only one variable coming in, and that variable you sample, and then you do some internal computation, and then if it is time yet, you do the U, otherwise you don't do the U, you go back and sample another U and so on. So this is pretty simple. It can be done in same way with Simulink or MATLAB or whatever. So now, what happens with imperative synchronous program, like in case of S12, for example, you actually assume that there is a timer that is ticking. So timer ticks, and then says time to sample. So you sample, you do the computation, then you go back and wait for the tick, and then you sample, and then you go for the tick, and then you sample, and so on. So what happens when you have multiple signals coming in, multiple flows coming in, and you wait for tick, and at the time of the tick, if a particular value has not arrived yet, then you count that as an absent. Now, how can you do that? The only way to do that is to have a very precise notion of timing, because if you know that at every 10 millisecond or every 20 millisecond or whatever your inputs will come in, only then you can determine that something is absent. But what if the thing that you're waiting for is stuck in a buffer in a router somewhere in the network? then you don't know whether that it is absent or it is on route to come in, and therefore the compositionality in an asynchronous environment becomes completely impossible in such situation. So if you have a completely time-driven, tick-driven synchronous programming, then you have to have very precise notion of what it means to have a value and what guarantee you have that that value, if it was present, it would be occurring at this time or not. If it doesn't occur at this time, then it will come in the next time, and that will actually give you a very different value and a very different output. And then that changed output will give rise to non-determinism, and the determinism will then the value that you get as the output will depend on external factors such as network delays and so on and so forth. So that's one problem with imperative synchronous programming that basically is something that we want to avoid. So let's see how we can handle this multiple inputs in this paradigm. So let's say this program also has another input called RPM. It's actually measuring the current RPM of the engine. And what it is doing is it's saying that change the thrust value with the whatever you have computed if your RPM is below a threshold. But if the RPM is not below the threshold, then put a default thrust, because you don't want to unnecessarily rev the engine unnecessarily. So that's the idea. So you have two inputs, V and RPM, so two flows coming in. But note that at the last data flow equation I've written, I'm saying that RPM has to be only sampled at the time when you are computing thrust, because you don't need the RPM any other time, because you are deciding whether your RPM, whether you should compute the thrust based on the integration that you have done, or you should put out a default value based on the RPM. In any other time that you are computing things, you don't need to sample the RPM. So you are saying that don't sample RPM unless you are actually computing U, and this basically allows you to avoid measuring something that you don't need to measure. That you don't need to measure. Moreover, if RPM is coming through, let's say you have this communication between this engine and the velocity meter are two different places, and they are coming through a bus or some kind of communication mechanism. You don't have to wait for RPM unless you know that you have to wait for RPM. Every time you don't have to synchronize. Every time you measure the velocity, you don't have to wait for the RPM values to come to you, because the RPM value is actually can be a subsample of the velocity value. So so in a sense, the computing of the sampling of RPM value is aligned with the sampling of velocity, except that not every time the velocity is sampled, but only when necessary, and therefore now you can think of this system as a sequence of reactions. So every time you measure a V, you compute something. You compute the error, you do the sum end of the integration, and then if it is time, you compute the U. If you have RPM sampled, then so you sample V, and then you go ahead and do the integration, and then you check if your count is 0. If your count is 0, you also sample RPM. And then, depending on what the RPM value is, you compute U, right? So you see that already the difference between Simulink or S2L is that first, I don't need to sample everything at a tick. My tick is actually velocity sampling. When I sample the velocity, I do all the computation. After that, if I feel the need, if a condition is satisfied, which is count equals 0, then I go ahead and sample RPM. And therefore, I am actually sampling in the middle of a reaction. I am not sampling everything in the beginning of the reaction, which is a tenet of Simulink or SRL, that you have to sample everything in the beginning of the reaction, then you have to compute the reaction. If something is absent, you have to treat that as absent and then go back and sample everything. In this programming model, you don't need to sample everything at the beginning of the reaction. You can sample as needed, when needed, in the middle of a reaction. But since this sampling of the RPM is still being done aligned with the sampling of V, because any reaction in which RPM will be sampled, V has already been sampled. So you can think of a reaction in this system is sampling of V, computation, then if needed sampling of RPM, then computation of U, and then back sampling of V, and then doing the computation and so on. So reactions are totally ordered. Reactions are ordered based on the sampling of V, because sampling of V is totally ordered, because V is a single signal. You cannot sample it in a partial order. You have to sample it, one after the other. So it's a total order. So logical time is still totally ordered. So still we are kind of like synchronous programming, because we are totally ordered timing model. Now the other problem with sampling like in SRL and Simulink is that, let's say you have many signals, and you know that all the signals have different time resolution. Some signals change very frequently. So if you go by Nyquist criteria, you have to sample at least twice as the highest frequency component and so on. So let's say we have discrete signals, and then they are spaced by, their change is spaced like the top bar, the arrows show when they change. Now you see that sometimes they change very intermittently, and sometimes they change very frequently. Now if you are doing sampling by tick, you have to put your tick's resolution as small as the smallest resolution, right? Because otherwise you will miss some of the changes. So even though these signals change very intermittently, except that only one or two places it has the smallest time resolution, you have to go by the smallest time resolution. That's a very bad, wasteful thing to do. So that's why you don't want to do a time-driven computation. You want to do an event-driven computation. So what you want to do is you want to actually only sample when there are events. That somehow you have to. Somebody tells you that there is an event that you need to sample. So now let's go back. Let's go to the issue that what we saw so far is that our reactions are still sequenced in a total order. Therefore, I can do the whole thing as a sequential program. Unfortunately, that there are cases when doing something in sequential order basically makes you make a design choice, which is not exactly what the model actually is telling you. So here I'll show some example. So for example, the car, when you are sampling the temperature, sampling the speed, it is also sampling various other things. It is sampling temperature for climate control. It is sampling user input to CD player. It is sampling GPS signal for navigation. It is sampling many other things. Do you have to sample all of them together? And the answer is no, because they don't have to be all taken care of at the same pace, so to speak. So you have to decide the pace at which the corresponding sampling has to be done, and the corresponding changes of the computations have to be done. And so let's look at this example where I have a cruise control like before, and then I have a thermostat controller, and for simplicity I also took a PI controller for thermostat controller, and they have two different threads or two different processes by which they are active. Now, if you have this, then it's best to have two different processes or two different threads to actually implement them. Now, the problem is that if you want to model this in a synchronous programming model, either you have to do completely two different processes, or you have to do them as single process, where you will be forced to sample both of the inputs at the same time. And that basically, as I said, will give rise to the wasteful thing. Now the question is that suppose now these two are not interacting at all, because this velocity sampler is computing thrust, this thing is computing your temperature control. So they don't have nothing to do with each other. So you can actually model them as two different processes, no problem. Now suppose your car has this special feature that when the temperature goes below a certain level, you want to disengage the cruise control because it may be freezing condition outside, right? Let's say the car is doing that. I mean, I'm not saying that a car designer will do that, but let's say you want to do that. Then you have to have interaction between what you compute there and what you compute there, because you have to tell the other guy when your temperature sampler finds that it's a too low a temperature, it has to tell him that disengage the cruise control and compute the thrust based on some other formula. So therefore, I have to have interaction between two threads or two processes, whatever it is. So let's, before we go into that complicated an example, let's take a very simple example. Let's say I have two data flows. One is Y is accumulation of X's, which means Y dollar init 0 means that Y is the last value of Y dollar is the last value of Y. So it basically, as you sample X, you accumulate it in Y. You do the summation in Y. And the second one is another one, which is accumulation of V in U. So you have these two different flows. These flows have nothing to do with each other. But let's say I want to actually implement this system as, this is my model. I have two flows. So one way to do that is to have two different threads, right? So one thread samples X and computes Y. Samples X, computes Y. Other thread samples V, computes U. Samples V, computes U. So they have nothing to do with each other. They can run at their own pace, so they are asynchronous with respect to each other, right? They don't have any interaction. But if you want to do, if you give this two data flows to Astral or even to simulate, what will happen is that they will assume that somehow that X and V are to be sampled together, right? And when you sample them together, you are forcing them, even though that V may have a value every now and then, but you are forcing it to actually have a value or to declare absence or whatever, and that will give rise to a problem that is that the implementation you will get from that is not exactly what this model is saying. This model is saying that I can have 50 X's before one V, or I can have 30 V's before one X. Doesn't matter, all such possibilities are allowed. But as soon as you put it in any synchronous programming environment and do code synthesis or do any other implementation, you will find that you are actually forcing these guys to actually synchronize somewhere in the middle, right? We are not preserving all possible properties. And if you look at this picture on the left side, what I'm showing here is that as long as the number of X's and V's on any path is the same, I should get the same output on both Y and U. And that is called a Poisson determinism. Basically what this means is that it's not deterministic, but as long as some boundary conditions are held, it is deterministic. So if in this case the number of X's and Y's, X's and V's being the same, in the sense that not the total number of X's and V's on any path and total number of X's and V's on another path, if they're the same, the output should be the same. So that's the notion of determinism in this. And with respect to that notion of determinism, the multi-threaded version is the only correct implementation. If you want to do this, if you want to make this total ordered system, then you have to decide when to read X and when to read V. If you want to read them both together, that's like simulate. If you want to read X first and then V, then what if the V is very frequent and X is not? And opposite is also true. So you cannot do any implementation that will allow all possible behaviors if compared to what you would get when you have two distinct threads. Now this is when they don't have any relationship at all. Things get now you can do various things. You can do buffer design and so on and so forth, but that requires some other information like effing clocks and so on. So let's not worry about that. Another way to do this is to do two different processes, but when you do two different processes in any of the other systems like Esterol or Lustre or whatever, if they don't talk to each other like this example, then the solution will be fine. But if they talk to each other, then modeling them as two different processes will not work, because then who will do the synchronization? Synchronization is not modeled in the system, and they cannot generate code automatically for synchronization. So I have to have a framework in which I should be able to express this kind of data flow where different flows have different paces, and they sometimes interact with each other. And when they interact with each other, there should be synchronization, and like mutex or semaphores and so on. So I should have my modeling and the synthesis system cognizant of the fact that there is synchronization. This synchronization has to be deterministic, and these are the conditions for synchronization. And only then I can generate code that is which has the proper synchronization structure and still multi-threaded. So here is how I will solve this problem where the temperature controller interrupts the cruise controller. And the idea here is that first I model the cruise controller slightly differently. I take a new input called interrupt, which is an interrupt that it is expecting, and the idea is that computation of is going to be interrupted, or U will be computed only when there is no interrupt. So if interrupt comes, then I would not put this new thrust value myself, and actually this is not a complete code. It has to go to a different behavior when the interrupt comes. So now the question is, how does it check for interrupt? Does it only check for interrupt when the count is equal to n, or does it check for interrupt at every time it does the velocity? It checks the velocity, because if the total number of iterations for the integration is large, then you might actually want to check the interrupt at every time you sample the velocity. But if the interrupt is not supposed to come that often, then you can check the interrupt when you actually start to compute U. But either way, if you do either of them, you still get a total order on this. So now the temperature control has to actually generate the interrupt. So it can generate the interrupt when the temperature goes below a certain value, and then you will get this interrupt is actually aligned with the temperature sampling, so it's still a total order. So we have two threads which have their own total order, but they share a variable, right? So the question is, how do they know that, deterministically know that they have to interact with each other? They have to stop for, like the other guy, let's say, is about to compute U. It has to know that I should check for interrupt. But this other guy has to know that when I generate an interrupt, I have to wait for the other guy to have read that interrupt, because otherwise, I cannot go ahead. So there are two asynchronous threads computing, but on this shared value interrupt, they have to synchronize. And so to do that, what we have done is we have created this spatial equations called interrupted, which is actually synchronized with the computation of U, and here the interrupt is synchronized with computation of theta, which is the temperature control. So what they know is that what this program knows is that this itself is not enough. I have to add one more thing, which is, where is it? So I have to basically tell the system that the count 1 equals n and count 2 equals n has to be synchronized. And once I have done that, I have told the system where to wait for synchronization. And so this gives rise to this what we call clock hierarchy. So here what we are showing is that I have two sampling rates, V and T. They are not related to each other. And then the various conditions are also subclocks of V and T. But this subclock, that is when count 1 becomes n, which means that U is supposed to be computed, and in the other one when count is equals m, when theta is supposed to be computed, I equated them as an extra condition, which means that that's the time when they should wait for each other. So which means if this thread has come to computing a queue, it knows that I'm waiting for an interrupt, so I should wait. And the other guy knows that if I have come to count equals n, I'm going to send an interrupt, either true or false value. So I should wait until that other thread synchronizes with me. Now the synchronization code is to be automatically generated. It's not in this model. So what this equation tells the program generator or code generator is that generate the whatever synchronization skeleton is needed for this synchronization to happen. So this is where the partial order comes in. So you see that the time is now partially ordered, except that at certain positions they come together, and therefore some non-ordered elements get ordered because of these spatial locations where the two partial orders, the union of two partial orders, get deterministic because of their shared variables. How much time do I have?
15.
Okay. So am I making any sense, or I'm just going on?
I have a question about actually you are stating some condition where you can make non-deterministic time here, the physical world, you want to make it using the logical, what we call logical time, deterministic, to be able to build deterministic model. Right?
Deterministic implementation.
Yeah, deterministic implementation. My question here is, my issue here is about the platform, the implementation platform here.
Yeah.
Because if you take this actually and you want to implement it on the platform.
Yeah. So I'm coming to that. Actually, the next is the calculus of that, and there we'll see what assumptions I'm making on platforms, and if the platform can deliver me those. Okay. So let's look at this. So okay. So let's say I have two polychronous processes, and I said that if I put them in this parallel, then I'm basically saying they are composed, right? So their common variables have to be synchronized on and so on and so forth. Now, if I want that so this is basically this parallelism is based on what I just explained, right? So P1 and P2, their partial orders are to be composed, and then based on these extra equations, I have to decide where these two partial orders overlap, and I have to do the synchronization. Now, if I want to put this thing in a synchronous environment, then in the synchronous environment, such as a platform, I need to show that I need to be able to prove that this P1 parallel P2, when put on that platform as an implementation, will actually make a deterministic execution, even though the platform has delays and other stuff, right? So is that what you're asking?
Yeah.
Okay. So the question is now, what does it mean to be the same behavior? So the same behavior we define as flow equivalence. So basically, what that means is that if your input infinite streams are the same, then your output infinite streams will be the same, right? So their timing doesn't matter. What matters is that if the input flows are the same, then the output flows are the same, right? So no matter what, if you have implemented it synchronously or in an asynchronous environment, If that condition is happening, then we say that they have flow equivalence, and then that's what we want.
Are you talking about the flow in the physical world, and that is standard understood?
No. I'm talking about the flow of values.
Or the sampling.
Sampling and the output actuations. Now, in the physical world, these actuations. So whether I implement it in a synchronous platform or a completely tightly synchronized platform, if the flows are the same, then their effect on the physical world should be the same, except that if the timing is not right, then they may not have the same effect. But let's assume that set aside the timing issue right now, and let's assume that when let's say the thrust values, right? Let's say the thrust values that I'm looking at. If my velocity inputs were the same, right? The velocity sequences of sample velocity is the same, and the thrust values that I compute should be the same, no matter how I implement it. Does it make sense?
Yeah, you talk about the computation correctness here.
Right.
There's
right.
no problem at that level.
No, but if you're multiple this P1, P2, P3, and so on, when I compose them, my model is actually polychronous, right? So I'm using the polychronous calculus and this timing and so on. When I implement them, I have my P1, P2, and P3 are actually not in the same kind of environment. It may be that they're on a network. P1 and P2 are communicating over a network where there are delays and so on. So I have to still prove that when I implement them on an asynchronous, unspecified delay environment, I should have the same values. That's the notion of flow equivalence. Now you are asking probably that when that thrust values actually go to the engine, do they do the same thing?
You have to be on the actuation, so it's not probably going to be the same. I mean, you do have some delay in the
right. So the delay might actually have a very different effect. Right. So that we are not talking about that. So there, in our most recent work, we looked into some of the ways to look at the real-time delays, but in this calculus we don't have real-time yet. So this is completely just value correctness, right? Okay, so this is what I'm talking about is if P1 parallel P2 in the model, the single bar is the model sense, is flow deterministic, then it is safe to implement. And if I put it in an unspecified asynchronous environment and compose them, if we can show flow equivalence, then the implementations are the same. And if they are not equivalent, then the question is, how do you generate wrappers around P1 and P2 to make them equivalent? So let's see. So let's take an example here. So let's say P1 is X, computing X, and P2 is computing Y, both based on the value of A and B. A and B are two signals or two flows. Now the default operator has this thing that if A comes, then A goes to X. If A doesn't come, then only B goes to X. So now, if I put X and Y in the model, then they are equivalent to X equals A default B and Y equals X, because they are actually the same equation. But if I put it in an asynchronous environment, A and B may be coming from different locations, and these two are being computed at different locations, so there may be delays. So in the first one, A may be coming first, and same A may be coming very late in Y, instead B might be coming, right? So in that case, if I put them in an asynchronous environment, then the answer may be different in the model level composition and the implementation level composition. So that's why in this case, P1 parallel P2 is not flow equivalent to P1 double parallel P2. So what I have to do is I have to do wrappers. So how do I do these wrappers? So suppose I have two extra Boolean signals. Somehow I create two extra Boolean signals CA and CB, which are synchronous. So A and B were not synchronous because nothing said they have to be sampled together. But I have CA and CB, two Booleans, which are coming from the same source as A and B. And these are saying that C and CB are saying both are 1 if both A and B have been sourced. If CA is 1 and CB is 0, then A has been sourced and B has not been sourced, and so on. So this is a way to tell the system that C and CB are basically precursors of A and B, and therefore I know exactly what to wait for. In that case, the only thing I have to worry about is CA and CB are being delivered in proper time and without loss. So one way to do that is to have something like a present system call. The question is, the present system call will tell you whether A and B are present. Unfortunately, whether your system actually have a deterministic system call that tells you present will be a question. So if the present system call doesn't work, then you can actually have one of the processes declared as a master process. So if the master process gets the values, then it tells the C and CB what the values of them should be. Then the other process makes completely aware of what's going on in the other process, and so then in that case also the asynchronous composition becomes flow equivalent. Now the next example, and I think I'm going to skip this because the next example shows that in this case actually what I'm doing here is that I am actually preserving the that A and B, if they're both present, I'm preserving that, and then if only A is present and not B is present, I'm preserving that. In the next example, what it shows is that you don't have to necessarily preserve them and still can get some sense of determinism, and which is by actually buffering them, and so that if A's and B's can overtake each other, but you know that the overtaking has a specified number of a limit on the overtaking, then also we can actually do the by properly designing the buffer, we can still preserve determinism. So that's what this was saying. So I guess I'm running out of time and probably not making a whole lot of sense here. So what we talked about is the polychrony and calculus of partially ordered logical instance, and then I slightly talked about at the end the calculus about how to refine the spec to an implementation to preserve the flow equivalence between the polychronous composition versus a synchronous composition, and then we didn't talk about the work that we are doing on this. So I have a list of references that might, if anybody is interested. So once you get the slides, you can actually look at them. Questions?
I have one question.
Yeah.
How do you have this synchronous data?
Yeah, so during the code generation, we use an assembly solver. So the only way it can deadlock is that so you have something, it depends on something, A depends on B and B depends on A. That's the deadlock situation. So what we do is when you compose, when you do the polychronous level composition, the delays are basically zero, right? So we basically assume that we first construct a graph, right? Yeah, but the loop is not necessarily always an indicator of a deadlock, because I haven't gone into this, but sometimes this dependence of A to B depends on something else. Like for example, remember like when I say U equals this, when count equals 0, and else something else, right? So the dependence of U on let's say V is modulo count equals 0. It may not depend on any V otherwise, right? And then V might depend on U, on count not equal to 0. Then it
Might
might
you get deadlocked just on some irrational counts, not even on the, if something goes wrong with your indexing scheme.
right. So what we'll do is, so the indexing scheme, let's say, so you have count equals n is a condition, right, under which there will be a dependency, right? And this guy is waiting on me because there is a dependency on this, but I will mark that as a predicate on which this dependency is valid, and then the counter dependency will have to be valid under some condition, right? So then I do an SMT, I submit that to an SMT solver. Now we may not be able to, depending on how complex the predicate is, the SMT solver may not be able to solve it. But if it is simple things like count equals 0, not equals 0, it's easy to solve. But so normally, if we don't find, if we cannot prove that it is deadlock free, we declare it as deadlock, and we redesign. We have to ask the programmer to redesign the system, because so we are sound but not complex. So if we say there is a deadlock, there is a deadlock. If we say there isn't a if we say there isn't a deadlock, there isn't a deadlock. But if we say there is a deadlock, there may not be a deadlock, because our SMT solver could not solve the constraint and therefore thought that it is possible to satisfy that loop.
So you're not sure about the formal verification of the system based on this?
Well, so the model, the Polychronous model, we have the French guys have. I have a different Polychronous modeling scheme called MRICDF than theirs, but they have a model checking tool called Sigali. So what it does is basically uses polynomial theory and polynomial equivalences. We have not implemented that in our system, but it is possible to do formal verification of various properties, but not necessarily all properties. But deadlock, the deadlock checking has to be done before code generation, because you don't want to generate code, because these deadlocks are often dependent on conditions, right? So you may not find them for a long time when you run the code until you hit that condition. So you have to be always be sound and not necessarily complete. So you have to throw away code which you cannot prove deadlock free.
Yeah, but with a model checker, you can forward verify that the system is deadlock free.
No. So it depends on your model checking tool, right? So if the condition under which the deadlock is valid is based on first order theory or first order predicate logic or something, you have to call an SMT solver, because you cannot. For example, let's say you are computing a function fx, right? And then you are saying that one of the in one place you say u equals something let's say v something when fx equals 0, right? Now this fx is a function that you have defined, right? Now we know that the given an arbitrary function, whether fx equals 0 is an undecidable problem, right? So you may not be able to do model checking or anything to actually disprove that deadlock. So in that case, what you have to do is you have to say that I assume that this fx can be 0 at some point, right? But if your fx has simple properties that you can express it in a simpler, let's say Presburger arithmetic or lesser arithmetic, then you can use an SMT solver to prove that, oh, this fx never gets 0, so this loop is not going to be valid. So just model checker will not do. You have to have more ability, more than model checking ability.
Then you can grill them in a round table.